Hello friends, welcome to this video on autocorrelation and its property. This video will now help you to define what is meant by autocorrelation, will state what are its properties, and we will see the problems in detail in the next video. We'll move on to the video. Autocorrelation of a random process. What does autocorrelation actually mean? Autocorrelation of a random process measures the correlation of a signal with a delayed copy of itself, quantifying the similarity between observation at different points in time. So, what we are measuring is the correlation of the signal. So, correlation. How is one signal related with the delayed copy of a version of itself, and how it is being measured? It is being measured at different points of time, and we notice what is the similarity between them. So, let x of t1 and x of t2 be two random processes. Then the autocorrelation of the random process is given as Rxx of t1 comma t2. This is how we denote it. Because there are going to be two random processes x and x taken, we have x and x. There are going to be two time members t1 and t2 involved in the process because we are measuring the difference in the signal with the delayed copy of itself. So delayed copy meaning at a different point of time. So we take or define it as the expected value of x of t1 product x of t2. So we compute the product of the two components x of t1 and x of t2 and then take expectation to the product, and the output we get is defined as the autocorrelation of the random process. It will be a function of your time. Okay, so we have a time t1 and t2 which is going to be the function of your random process. In case we have this random process to be either a strict sense stationary process or a wide sense stationary process. We have seen about triple S and double S in our prior videos on random processes, where we say a process is going to be a WSS if its mean is going to be a constant and autocorrelation is a function of tau. So we know that for a WSS or a triple S, the autocorrelation is obviously going to be a function of tau. What does tau mean? Tau is nothing but the time difference. So how do we measure this time difference? T1 is my first time parameter, T2 is the second time parameter. I take the difference in time between them, bigger number minus the smaller number, and this time difference is denoted by tau. So if it is a triple S or a WS, automatically this autocorrelation becomes a function of tau. So we directly write Rxx to be a function of tau. It can be written as single x or because both the components come from the same capital X of x which is going to be the random process. Or we drop the x also and then we write it as R of tau. And we write it as x of t into x of t plus tau. So what happens now between the time difference? So time difference is t plus tau, one time parameter. T is the second time parameter. When I consider the difference between them, subtract the bigger number minus smaller number, what you are left out with will be tau. So this tau is what we are denoting it over here. So if you compute it as a function of tau, you write it as x of t into x of t plus tau. And we notice that the subtraction or the difference between the two time parameters gives us the input value which is going to be equal to tau. This is how we define the autocorrelation of a random process. Pictorially, if we want to represent it as a cycle, what we do first is select process values. So we select x of t1 to be one time process and x of t2 to be the second time process. What happens in the second stage? We calculate the product between them. So we calculate x of t1 product x of t2. In step 3, what do? We compute the expected value out of it. What is expected value? E of x of t1 product x of t2. And what does this now give? It gives you the autocorrelation Rxx of T1, T2, which can be analyzed for the inputs of the data. So this is what we call it as an autocorrelation cycle. Now we will move on to properties of autocorrelation. The first property says the mean square value of the random process may be obtained from the autocorrelation function Rxx of tau by substituting tau as 0. Now what is going to be my Rxx of tau? This is my Rxx of tau. What happens with my Rxx of tau? What I am going to do is I am going to substitute tau as 0. In my Rxx of tau, as tau, here tau is here, you put this as 0. So what you will have is E of x of t into x of t. But how I can write this as? I can write this as E of x square of t. And what do you call this E of x square t as? You call it as the mean square value. Okay, so what do you mean by mean square value? In Rxx of tau, when you put tau as 0, the quantity which you get will be called as mean square value. This is a very important quantity which will be helpful for us in determining the value of variance of a data and average value of any power of a signal. So average power of the signal is always calculated using the mean square value E of x square of t. So practically this plays very important role. So we will try to memorize it. The second property states that Rxx of tau is an even function of tau. What do we mean by an even function? Whenever my x is replaced with that of minus x, if the output is going to be the same, then you call the function to be even function. So what happens if this tau is replaced as minus tau? I still get the same answer as my Rxx of tau. So it is a function of which variable? Tau. So you call Rxx of tau is an even function of tau. Property number 3, the maximum value of Rxx of tau is attained at the point tau equal to 0. Okay, so we say that the autocorrelation value is always lesser than or equal to Rxx of 0. What is this Rxx of 0? Mean square value. So it has already reached the top, like it is going to be the topmost value of all the data collections which we have. So the autocorrelation function, when you have too many data, what is going to be the topmost value? It is attained at the point tau is equal to 0. Property number 4, if the random process x of t has no periodic components, then the mean E of x of t, which is denoted by mu x, is given by the formula limit n tending to infinity Rxx of tau the whole square root. So for a random process, how to obtain the mean of the random process using the autocorrelation function? So you just allow limit n tend to infinity in your autocorrelation and take square root of it. It gives you the mean value. So this mean value and the mean square value which we noticed over here are the two components which will help us to estimate the variance of a data, because we know that what is going to be variance of any data? Variance of x is nothing but E of x square minus E of x the whole square. So what is this E of x square? This is nothing but our mean square value. And what is this E of x? This is what we have estimated here as mu x. So in order to compute your variance, we will be requiring these two formulas, which is got from property number 4 and our property number 1. Okay, so we will be using them frequently. So try to memorize them. Property number 5 states the autocorrelation function of a random process cannot have an arbitrary shape. So it doesn't have any shape on its own. It takes the shape of your function which has been defined. Property number 6 says if x of t is periodic, its autocorrelation is also periodic with the same period. Okay, so if the random process is periodic with the same periodicity pi, so after every pi units the process gets repeated, then the autocorrelation function Rxx of tau will also repeat itself after how many units of time? After pi units of time. After a period time, it will also be repeating itself. Periodicity means the process or the graph repeats itself. Okay, so the function is going to be repeating itself after a certain amount of time. You can call your sine x, your cos x, all of them are going to be periodic in nature, meaning after a certain amount of time, the curve is going to repeat itself. So it drops and stops over here. What happens next? Again, the same graph is repeated as it starts and stops over here. Okay, so this is what you call it as periodicity. So after how much of a period it is going to repeat for the random process, the autocorrelation function also repeats after itself of the same process. So these are going to be few properties of your autocorrelation function. In the next video, we will see how to apply these properties to evaluate problems in autocorrelation function. Thank you.